All right, so as you can see, electron configuration. So not going to lie, this is a difficult topic. It's hard. The idea of electron configuration, or the reason we need it, is because earlier when we studied the Bohr model, right? We say in the Bohr model that we have a nucleus, and inside that nucleus are protons and neutrons. And then we have these electrons that orbit like planets around the sun. And how great would it be if they were nice and orderly, and every 365 days of the year they made their way around, right? But we really know it's more like a cloud. And so electron configuration helps us to understand about the energy of those electrons in that cloud. But what it also does is this. There are electrons, according to Bohr, here, here, and here. And Bohr would say, as you move away from the nucleus, that energy definitely always increases. And it's probably tough to read, but that's all right, you're hearing me. So energy increases as you move away. Now, electron configuration actually helps us to disprove this idea. Believe it or not, sometimes an electron, such as like this one, the second level, might be more energetic than that one. And so, we have this thing called electron configuration. Now, the first thing I do whenever I do electron configuration is I make this little cheat table. So I suggest you do it too. There are 7 rows to the periodic table. And it is not a coincidence that the Bohr model contains 7 quantum energy levels. What do I mean by quantum energy level? I mean, if that's the nucleus, the first quantum energy level is that one. Then the second, third, fourth, fifth, sixth, and seventh. Well, the same thing is going to happen here with electron configuration, and we're going to number the levels. So the first thing I do is I put an axis. So anytime we graph, we always want to label things. And this axis is going to be distance from the nucleus. And just like I told you, there are 7 rows in the periodic table, so therefore there are 7 quantum energy levels. 1, 2, 3, 4, 5, 6, and 7. Now, each of these quantum energy levels has electrons that are found in certain configurations. And those configurations become more complex as you move up. So the first configuration, and the simplest one, is called an S configuration. What S stands for is spherical. Now what does that really mean? It means this. We were to set up a graph, and we were to make the axis right there, the nucleus. Because we know protons and neutrons are in here, and we just care about electrons right now. It means in the first level of the Bohr model, so if you draw a little circle, this would be a sphere. That's why we give it an S name, and it's a ball, so you got to think 3-dimensionally right now. In any orbital, 2 electrons will fit inside of it. And so what we would do is if we were going to find these electrons, 1 and 2, is we go find that first energy level, and we look somewhere inside that ball. 2 electrons are possible there, therefore it's 1 spherical orbital with 2 possible electrons in it. At the second level, it gets more complicated, and I'm going to keep drawing a little bit, because otherwise the drawing just gets a little too messy. There are also s orbitals, so a bigger sphere, a bigger ball. And again, 1 orbital with 2 electrons in it. But here's the thing about 2, right? The second level gets 2 types of orbitals. The second type of orbital is called a pi orbital. Thus, we give them the initial of p. And when we think about these guys, we have to draw 3 axes: an x, a y, and a z. Pi-shaped orbitals look like figure 8s. Now they don't actually exist, it's just where you go find the orbitals, or the electrons. So the first one looks like this. And I just said inside of any orbital you can fit a maximum of 2 electrons. So one of them would float somewhere in here. And then the other one floats somewhere in here. 1, 2 for this 1 p of x orbital. Likewise, there's a p of y orbital. One electron fits in there, one in there. So if I was looking for these electrons, that's where I would go. Then likewise, last one is on the Z, so man, this gets nasty. An electron and an electron. For a total of 3 orbitals, 2 electrons each, for a total of 6. So that next one is 2p6. Likewise, at the third level, there is an s orbital. It would have 2 electrons in it, because all s orbitals have 2 electrons. Okay, so you go find those 2. Likewise, there is a p, 3p. It looks just like this, they'd just be a little bigger. I'm not going to draw them because, boy, this would get nasty. So 3p6. Because it's the third level, not only of s's and p's, you also get d's. Doing these would require me to have a 5-dimensional board. Don't have it, ask the superintendent, we don't have it. So a 5-dimensional board, but if it was 2 electrons per orbit, that would be 5 times 2 for a total of 10 electrons possible. Not a coincidence that at the third level, there are 3 types of orbitals. So we can make a little prediction. At the 4th level, there would be 4 s's, p's, d's, and the last level, 7-dimensional, called F. 7-dimensional, 7 orbitals, times 2 each, just like these, for a total of 14. Here, 5s2, 5p6, 5d10, 5f14. And now you might ask yourself, Mr. Gerbe, should I write a 5g here? Yeah, you should, but here's the thing. There are no electrons and no elements that actually exist at that level. So you know what? Just ignore them. Act like they're not even there. 6s2, 6p6, 6d10. Now, again, you might want to write a 6f14. You might want to write 6g, 6h. They don't actually exist. There's no electrons, no elements found there, so why bother with them? Here, 7s2, 7p6. There's nothing found at 7d or anywhere else. Now, here's why this is important. So this is like the glue, this whole thing. Let's see what time we're at real quick. 7.5 minutes. All right, so Bohr model says as you move away from the nucleus, energy has to increase, right? Wrong. This one means the first level outside the nucleus. And he's right on the first level. So you got to think kind of like a typewriter here. You draw an arrow, and you get to this line, and that thing chains you back to the next diagonal. So 1s2 is the most energy, or the least energy, I should say. Then 2s2, meaning it's found at the second level outside the nucleus, and it's in that spherical orbital. 2p6. So far, 1, then 2. It kind of makes sense, right? S, then P. 3s means it's at the third level outside the nucleus. So far, so good. 3, 4. And here's your kicker. 4s2 would be found at the 4th energy level. So maybe it's that electron right there. But if you ching back here, you get 3d10. And it's the 3 that matters right here. This has more energy, because we're doing increasing energy with our diagonal arrows. This 3d has more energy than 4s. What does that mean? It means something that's tucked inside here in the 3rd energy level actually has more energy than something back here in the 4th. Now it gets even better. 4p6, 5s2, right? So now we're at the 5th energy level, back inside of the 4th. 4, more energy than a 5. Bohr model, gone. 5p6, 6s2, 4f14. Meaning something in the 4th energy level has more energy than something all the way out in the 6th. Then 5f14, 6d10. Oh wait, you know what? 4f14, 5d10, 6p6, 7s2, and then 5f14, 6d10, 7p6. So the most energy is found in the 7th level. That would have been expected by Bohr. but you can see these little embedded where a 5 has more energy than a 6. A 4 has more energy than a 6. And so because of that, electron configuration disproves Niels Bohr. All right, let's actually do an electron configuration and show you what the process looks like. So what you do on an electron configuration, and as long as you can make this chart, boy, it's awesome. It is very simple. So let's start with a simple one. We'll pick magnesium. So when you look at Mg, magnesium, this is electron configuration, meaning we only care about electrons. So the atomic number of magnesium is 12, therefore this thing has 12 electrons. So here we go. We start at 1s, always. How many electrons fit in that first S-shaped orbital? 2 do. Well, we got to get to 12, so we need them both. So there's 2. Ching back. 2 at the second quantum energy level, S-shaped orbital, there will be 2 that will fit. Well, we've got 2 already. And if we put 2 more, that gives us a total of 4. Well, we got to go all the way to 12. So 2s2, back to the beginning. We get to here, 2p, and 6 will fit in here. So we take a look at it, we say, okay, 2, 4, plus another 6 for a total of 10. Well, we got to get to 12, right? So that brings us to 3s. At the 3s level, 2 will fit. You've already placed 2, 4, 10. You need to put 2 more. They both will fit. 3s2. And that is the electron configuration for magnesium. What does this mean? It means if we started with energy and we increased it as we went. So energy increase means, for this one, Bohr was right. So we moved to the right, it increased. So first level outside the nucleus, second level, third. So for nucleus, awesome. But then if we look at something more, the next level, how about 21 scandium? So Sc, which has 21 electrons. So here we go. 1s2, 2s2, 2p6, 3s2. Now why am I kind of going fast? Because 2, 4, 10, 12, I gotta get to 21. So after 3s2 comes 3p6, and I need those two. 2, 4, 10, 12, 18, which brought us to 4s2, right? 2, 4, 10, 12, 18, 20. I got to get to 21. So after 4s, chain back to here, and now we're back to 3d1. What does it mean? This one electron at the third energy level has more energy than these 2 electrons out at the 4th level, disproving Bohr. So this is the electron configuration for scandium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. All right, let's do a monster electron configuration. We'll do it fast. So we'll pick one that's really hard. Praseodymium is 59, element 59. So praseodymium means that it's 59 electrons, right? You always start at the beginning. So 1, 2 will fit, 1s2. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now, why am I going that far? Because I'm just following the arrows. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Now, why am I still going? Because 2, 4, 10, 12, 18, 20, 30, 36, 38, and I got to get to 59. So 5s2, then 4d10, so maybe we got to move out here. Okay, so now we got to pay a little more attention because we're getting closer. We said 2, 4, 10, 12, 18, 20, 30, 36, 38. We're at 48. We got 11 to go. So after 4d10, 5p6. We now have 5 left to go. 6s2. We now have 3 left to go. We come back in here, 4f3. 14 would have fit, but we only needed 3 because 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 59. not a coincidence it matches there.